Hello, everyone, and welcome to today's webinar on maximizing transfer switch reliability. For today's webinar, you can expect to become familiar with evaluating different switching technologies, compare and contrast in-phase versus delay and neutral, and understand the impact of fault current on selection and design. For today's webinar, I want to invite you to use the question box. We are going to have a shorter Q&A at the end of this session because we do have another session, but we are still going to answer those questions or get back to you via email. Get ready for polls. We're going to have a couple throughout. If you can go ahead and answer when prompted. You'll get an exit survey as you leave the webinar today if you can fill that in. And the last thing I want to let you know is that you'll get a post-event email with a link to request your free in-person training. This is the training where you get those continuing education credits. We come to you in person, a link to future webinars if you want to register for more, and a link to the recording of this live webinar as well. My name is Laura Unger. I'm Industrial Manager here at Generac Power Systems, and at this point, I'd like to introduce our presenter, Michael Kirkner. Michael, thanks for being here.
Oh, thank you. So from a transfer switch standpoint, we can configure transfer switch systems in multiple configurations. This shows a single transfer switch, backing up all of the load. In this particular case, the transfer switch would need to be 2,000 amps to match the larger of the two breakers feeding it. Transfer switches can also be set up where we're not backing up all of the loads, we're just backing up part of the facility loads and we're just feeding it off of a sub panel. In this particular case, the transfer switch would have to be set up for 400 amps. It's quite common for us to see multiple transfer switches used on a given project. The reason for multiple transfer switches is obviously one reason is separation of circuits. In this particular case, critical could be an emergency system transfer switch that needs to be separated from maybe essential equipment. So what's a transfer switch look like? Well, it depends. I mean, the look of a transfer switch can be varied because there's varied switching technologies that can be used. The one on the far left is contactor technology. The one towards the middle is molded case, and then you can see two power breakers. The ones on the right are some smaller switches using contactor technology as well. So depending on what technology is used, the look of the switch can change. So our first polling question.
Question is, what is your preferred ATS switching technology? We're going to launch the question and you can go ahead and put your answers in. Options are contactor, power or insulated case breakers, molded case breakers, or uncertain. We'll give a few more seconds to collect responses here. I see them coming in. All right, and it looks like most of you went with contactor, with 51% choosing that as their preferred ATS switching technology.
We would agree with that position. Contactors provide excellent cyclic robustness, so they're really made to switch. So that's really what they do well. They're generally a good value in the market. Their price points pretty much there. One of the things that contactor technology struggles with is very high withstand and close ratings, the KA ratings. So breakers tend to be positioned a little bit better when it comes to the withstand and close ratings. Power breakers are okay for operational robustness, but they're really designed to extinguish fault current. Now, a power breaker is a little more robust than an insulated case breaker, so that technology can actually come in two varieties. So if it's actually a 1066 power breaker, it's more of a renewable device, so it's a little more robust than just an insulated case breaker. They're not really cost effective below 2,000 amps. So you tend to see power breakers used at 2,000, 3,000, 4,000 amps. Excellent withstand ratings. And it's very easy when you use a breaker style transfer switch to integrate a service entrance function because the trip unit for the utility side can be built right into the breaker. That kind of brings in where the molded case team seems to show up. It seems to show up in service entrance rated switches under 1,000 amps, where you're looking to establish, maybe a good cost point, also a good 65 kA rating. But from a general pecking order, I would kind of put the technologies in the order they're listed on the page. Contactor is most preferred. Then for big switches, maybe power breakers, and then molded case is more of a value leader switch for service entrance applications. Most of the switches in the market are standard open transition, which means there's always an interruption of the load. It's a break before make transfer switch. So when we're transferring back to the utility, you're always going to see a blink of the lights. Open transition is used the most because it's just the most cost effective. And the mechanical interlock that's built into open transition switches means there's no utility hassles, no interconnect issues to work through with the utility. And standard open transition switches can be configured in multiple switch configurations, which we'll explore as we go forward. So when we talk about the operating sequence for a transfer switch, one of the first things that a transfer switch has to do is delay when the utility fails. Usually that's about a 2-second delay. It allows the utility reclosures to try to reclose and clear the fault and bring power back. So we can't have this real long because we wouldn't make a 10-second start, but we don't want it real short because we don't want the generators to crank every time the lights flicker. At some point, the transfer switch is going to send the signal to start the generator. Historically, that was a 2-wire start, but we've seen with changes to NEC 700 that they want the 2-wire start signal to be protected against an open circuit or a short circuit. So that means that circuit now is usually going to be 3 or 4 wires to basically start the generator with both a normally open and a normally closed contact. At some point, we're going to transfer to the generator. Generator is going to pick up the load. And eventually the utility will return, and then we wait to transfer back to utility. Typically, at this point, we wait for a period of about 20 minutes. What we're doing is waiting for stability in the utility. Utility power kind of is at its most vulnerable point right now. There just was an outage. There's something going on with the utility. So let's stay on the generator and make sure the utility achieves a point of stability and reliability. Also for diesel units, we're using up some of that stale diesel, and we're actually helping the diesel engine be more healthy because we're actually carrying load on it. So for a lot of reasons, there's a good story around keeping that timer up. And then eventually we're going to transfer back and go into cool down. So we're going to have some discussions here in the coming slides about that process of transferring back between 2 live sources, because at the point of retransfer, both the generator and the utility are in a live condition. And then a couple, 2 minutes or so for the generator to cool down, and then we're going to shut it off.
That brings us to our second polling question. What is your preferred ATS switching method? We're going to put the answers on the screen if you want to go ahead and put those in. Options are open transition in phase, open transition delay in neutral, closed transition, or uncertain. We'll give you a little bit more time here to put your answers in. All right. And it looks like most of you chose open transition in phase for your preferred ATS switching method.
I would agree with that for what I would call general applications, but we're going to discover that there are some applications that maybe delay in neutral may be a better choice. So we're going to explore that option a little bit more. So the concept of delay in neutral basically means when we're transferring back from the generator to the utility source, the switch is going to get to a disconnected point halfway in the transition between the two, and it's just going to hold there for a few seconds. And the point to holding there for a few seconds is really to allow the loads to fully decay and turn off. So it's really designed to have the loads, achieve a full off state before picking up the utility source. The in-phase approach is more hopping from one source onto the other. Basically, as quickly as we can switching from the generator source to the utility source. So that really requires the sine waves to come in alignment. When we see the alignment of the sine waves, you transfer across as quickly as possible. So the difference between the two from an end user perspective is one, the lights flick off for maybe 2 seconds. The other, the lights blink for about 100 milliseconds or 0.1 seconds. So typically in-phase technology is implemented with a type of switching technology, usually called a two-position switch. They tend to operate a little bit faster. They tend to leverage themselves to only supporting in-phase operation. So they become an in-phase only switch. They don't have the ability to load shed or go to a disconnected state like that neutral state and stay there. And they tend to be a little bit lower cost. So they work well for general applications. Operating a switch in a delay and neutral functionality really is aligned better when we have a concentration of heavy motor loads, or if we find that we have nonlinear loads like UPS technology or VFD technology that has a large concentration of harmonic filters. So the concern with motors is the residual voltage. So motors, in the time it takes to switch to transfer, will maintain, if it's all motor loads, the voltage on the terminals of the motor. But the motors, if they're on a high torque load, will be slowing down. That means in the time it takes to switch to transfer across, the motors are starting to pull out of phase, and when you close into the new source, there could be a surge of current. So the idea with time delay neutral is, instead of taking any risks with that, just go to a off state and let the motors decay fully. So a three-position switch is typically used for time delay neutral. Three-position switches operate a little bit slower, so they can support in-phase and time delay neutral and load shedding. So they're a little bit more universal switch, a three-position switch. So that's kind of what we're dealing with there. So I would say typically we would see in the small kW market, small amp market, 400 amps and below, a lot of two-position, a lot of in-phase only switches. As we move into the larger switch market, you see more three-position switches are common that give more flexibility for application. So now we're going to explore some different switch functions. One of the types of switches that we see real commonly in the market is a service entrance rated switch. It's a switch that integrates overcurrent protection inside of the switch. These are typically used for a lot of retrofit applications where we're going to pick up the whole building, but there's no room in the building for dropping the transfer switch. So you put a service entrance rated switch outdoor in a NEMA 3R box. Service entrance rated switches can be implemented using different technologies. Kind of the premium way to do it is a contactor paired with a breaker, which is shown on the switch on the left, or it can be implemented with 2 circuit breakers. So different implementations for service entrance rated. Bypass switches we see in the market, typically in the data market and maybe the critical circuit in healthcare. So we see a lot of transfer switches that have bypass functionality when continuity of power is very important. So a bypass has the ability to rack out such that we can service the transfer switch without actually taking an interruption of power. Here's a picture of a bypass transfer switch. So the top mechanism there is actually the bypass. The bottom mechanism is actually the transfer switch, which can be racked out and serviced or tested. So as I mentioned, the primary markets that we see, data market, data applications, I would say is the #1 application. Healthcare, probably #2. But they tend to be pricey. Bypass switches usually about 3 times the cost of a normal transfer switch. So they're only utilized where the customer's seeing the benefit of that enhanced functionality in comparison to the price. Closed transition switches aren't very common in the market. They basically are a make before break transfer switch. They're actually going to wait for the sine waves of the utility and the generator to overlap. When they overlap, we actually connect the utility to the generator for about less than 100 milliseconds and then clear the generator off. The benefit of this approach is there's no blink of the lights on retransfer to the utility. So that's a benefit. The disadvantage is now I'm dealing with utility interconnect requirements, so I'm going to have to work through some of those issues. Typically, you set the generator a little bit faster than utility, so we get good repeatable in-phase conditions every 0.1 millisecond. I'm sorry, every 10 seconds you would come in phase if you were set to 60.1 hertz. You always want to put a shunt trip on the breaker feeding a closed transfer switch, because if something happens to this switch, we do want the ability to trip it off the grid. So we should take the protection that's in the transfer switch and tie it back to a shunt trip on the generator breaker. So one of the things we want to explore a little bit is fault current ratings. And when we look at fault current ratings for transfer switches, they really come in three varieties here. So really, the discussion starts with how much fault current do I have on site? A quick initial estimate is you look at the transformer rated amps divided by its subtransient reactance, and you get some general idea of the available fault current. Typically, transformer reactance is around 5%. So take rated amps times 20 and you're in the general ballpark. That is the maximum fault current that we're going to see right at the transformer. The cabling from the transformer to the distribution panels, and then from the distribution breakers to the transfer switches is going to attenuate that. So when you plug the elements into your SKM software, you can actually calculate the available fault current at the transfer switch. So at that point, you need to make sure your transfer switch has enough fault current for what's available in that point in the system. So transfer switches generally have three main ratings: a fuse rating, a coordinated breaker rating, and a 3-cycle rating. Current limiting breaker ratings aren't as common. They're pretty rare, actually. So what's changing between these three is time. Fuses open very quickly, so they give you very high fault current ratings. Typical fuse ratings are typically 200 kA, but a lot of people don't like to use fuses because you got to replace a fuse instead of just closing a breaker. So that drops you into the manufacturer specific breaker rating. Typically, those ratings are usually somewhere between 1.5 and 2 cycles. So they're going to give us a little more fault current capability than a 3-cycle rating. A 3-cycle rating is also called an any breaker rating. So you don't have to make sure the breaker's on a list if you use a 3-cycle rating, but you're going to find that the 3-cycle rating from a KA standpoint is a little bit lower than the coordinated breaker rating.
All right, our third polling question. What is your preferred ATS configuration? We're going to open up the answers here. You can go ahead and put yours in. Non-separately derived 3-pole, separately derived 4-pole, depends on the application, or uncertain. We'll give you a few more seconds as we collect those answers here. All right, and it looks like this one, everyone answered a little bit spread out here, with most choosing depends on the application.
I would totally agree with that because there's some applications I'm going to go 3-pole, and there's some applications I really need to go 4-pole. So a 3-pole transfer switch doesn't switch to neutral, and we achieve a single bond point at the service. It's typically the most cost-effective solution. And since we're not switching to neutral, the bonding and grounding for the neutral is actually very well preserved. So this tends to be the first choice approach unless there's an application hitch where that's not going to work very well. So when we look at a 4-pole switch, we're actually creating 2 points of bond, one at the service and one at the generator. So they actually use different bond points depending on which source we're running on. So the main reason to use a 4-pole transfer switch is if we're backing up multiple buildings, we don't want the buildings each to have a bond, and then when we're running on the generator, we create multiple points of bond in the system. So the whole point is by using a 4-pole switch, we take that situation, and when we back up multiple services or multiple buildings, anytime we have more than one service on a generator, we really need to be switching to 4-pole transfer switches. The other time we see it is in healthcare. Healthcare, once we're over 1,000 amps on the service, the feeders underneath the service also have GFP, ground fault protection. If you don't switch to 4-pole switches in that case, you find that your neutral current can actually flow back through the utility side when it's running on the generator, and it can actually create some false ground fault trips on those utility feeder breakers. So we see a lot of 4-pole transfer switches in the healthcare market as a direct result of that.
All right, and at this point, we're going to take some audience questions here. Do you use 4-pole ATS when you have a service with GFP?
Just because you have a service with GFP does not force you into a 4-pole system. Basically, the ground fault on the service isn't impacted by the use of 3-pole, so it doesn't create a false ground fault trip on the service. The only way the service is going to have a ground fault trip is if there's an actual ground fault in the system. So it doesn't create a nuisance trip.
Do typical ATS monitor all 3 phases?
Yeah, that's pretty standard today. Years ago, 30 years ago, you would typically get an average of the 3 phases when you were using analog switches. But today with the digital controllers, most transfer switches monitor all 3 phases separately.
Can you give your opinion on overlapping neutral technology?
Overlapping neutral, the way I kind of look at it is it's a solution for a problem that really doesn't manifest itself in the real world. There's a theoretical argument put forth around the idea of an overlapping neutral, but what happens is the transfer switch becomes much more complex to make the 4th pole operate differently than the main 3 poles. And we don't actually see the effect that's trying to be solved on 4-pole switches. We don't get nuisance tripping on 4-pole switches in 3-phase systems. So given the huge population of 4-pole switches and no proven cases of issues there, I would say stay with the standard proven 4-pole technology and don't add the added complexity because it doesn't seem to be warranted in the field.
All right, and like I mentioned at the beginning of this webinar, we do need to head out a little early for another session. I want to leave you with a few notes. If we were unable to get to your question today, please send us an email to indweb@generac.com and we can make sure that those questions are answered for you. I want to remind you that you'll be taking an exit survey as you leave the webinar today. Please go ahead and put your answers in there when prompted. And then tomorrow you'll be getting an email sent to you with a link to the recording of this webinar, as well as a link to request your free in-person PDSS class. This is the class where we come to you and you get those continuing education credits. I want to thank everyone for joining us today and have a wonderful rest of your afternoon.